something wrong. Okay. Hear me now? Okay. Sorry about that. So you missed everything I said before. Well, it wasn't important. Okay. This is, well, to introduce me and what I do. So I actually work in imaging. A couple of you I already know. And our research involves imaging using PET and MRI and CT, pretty much everything but ultrasound, in three main areas: neurology, so brain primarily, orthopedics. So we're doing work with MRI of the knee with people in exercise and sports science at UNC, and cancer imaging using combined PET and MRI imaging. And, you know, we're interested in both things kind of traditionally in the realm of imaging and then some of the newer stuff in deep learning and things like that. So if that's what I do, then, you know, well, a lot of image processing derives from the things we talk about in signal processing. So that's kind of how we come to signal processing. A lot of the math is the same, just different dimensions and things like that. And over time, you know, we're focused on time domain signals in this class, but I'll refer to things that relate to imaging as well along the way. So that's kind of where I come from. Okay. Now, oh, we're going to try something. We're going to have a little poll. Okay. So, never done this before. See if it works. Okay. So you should have access to a poll here, just kind of about your prior classes and things. And so, go ahead and respond to the poll and we'll kind of see where we're starting from here. Since this is the first group in our new curriculum taking this course, things are, well, from my perspective, the group is maybe a little bit different. So we'll see what we have to work with here. All right, this seems to be working. Thank you. Okay, results are in. Okay, so let's see. Okay, you took, so most of you took linear systems last semester, which is good. And that's, you know, I say that because this course works best for people when they take it immediately after, as things used to be in our older curriculum, but is not necessarily the case anymore. A couple of you, you know, you'll probably have to brush up a little bit, but we start the course kind of going into linear systems from my perspective and a perspective that relates kind of more specifically to this class, which so it should be fine, even if you've never taken a course in linear systems. We've had grad students who've been in that situation before. And, you know, again, we go over the stuff you need at the beginning. Let me know, you know, if I can help you a little bit in catching up on that. Probability and statistics used to be a prerequisite for this course, but since that's no longer required in our BME program, although I objected to that, it's helpful, but again, we'll kind of go over the concepts that you need. Almost everybody has seen probability and statistics. If you've not taken it, but well, again, if you're in BME, you've been at least a little exposed to it. They told me they would try to expose you to probability and statistics in some of the other BME classes. You'll catch up. And again, if there are concepts that you're a little weak on, let me know. About roughly half and half or so on the BME instrumentation course. So some things we talk about here will overlap or look a little bit familiar from the instrumentation course. And that's fine. Some of the things we talk about here relate a lot to control systems, but with a different purpose. So one of you will see some familiar things, although some of the language is different, and so don't get too caught up in that, but that's fine too. Number 5, this is always my favorite question. Your feeling about your experience with convolution and Fourier analysis relating to signals and systems. So usually people come out of that linear systems course feeling this way in the middle here. And we see a lot of that. Or, don't understand the mathematics very well. And this is typical, because it really takes 2 courses to really see what this stuff is all about. So the point here is that generally people take linear systems and work with transforms and Fourier analysis and convolution and see that it's math, right? And it's, you can kind of program yourself to do some of those operations, but for the most part, it's not clear what it's for. And that's what this course is about. Okay, so here we're going to talk more deeply about what it is all for and why it is all useful. And that's what we're going to get to. Okay. Okay. Thank you for your poll results. That's more or less what I expected. So no big surprises there. And again, and this is typical in BME, people come from slightly, different experiences, different courses, and we try to get you all to the same place, and we will. Okay. So now what I want to do, and oh, by the way, if you have a question, the best way to do that is probably to turn on your mic and speak up, because that's the way I'm most likely to recognize you. Okay, so the little raising hand thing, it's very easy to miss that. So I'm not trying to ignore you, but sometimes we just don't see these things. Okay. We're going to start with a little bit of introductory topics here, just kind of to set where we are. I'm kind of doing things a little bit out of order here, but we'll get there. So, okay, so this class is biomedical signal processing, and the linear systems course is sometimes called signals and systems. And so, everything here we're talking about signals, right? So what is a signal? Other than when you see it, if we wanted to give it a kind of general definition, it's basically anything you can put on a graph, maybe. change of some number of dependent variables with respect to changes in some number of independent variables. That kind of describes a graph or multiple graphs. And so in terms of a signal, we usually think of time signals, where time is the independent variable. And then there's some y-axis dependent variable, which could be any number of things, right, depending on what it is you're measuring. And so, you know, we kind of tend to leave that very general, and frankly, it doesn't really matter, at least in terms of the kind of analysis that we're doing. Still, always good to label your graphs, and I'll remind you of that over and over again in this course. Okay, but there are signals that don't fit that, right? There are non-temporal signals where this is not time, but something else, space, right? And, you know, it could be a variety of different things. It doesn't have to be time, and yet we can use the same kind of analysis if it applies, whether it's time or not. Okay, so keep that in mind. This isn't necessarily just reserved for time. Single independent variable and multiple dependent variables. So that would be a case where we have multiple signals that are tied together. Think of a multi-lead ECG or EEG signals where they have electrodes all over the head, things like that. They're measured simultaneously. But the relationships between them, all of those different signals are important, right? You can do things with regarding the relationships between multiple signals that you can't do by just looking at individual ones. And then it's possible to have multiple independent variables and a single dependent variable. And best example of that is a two-dimensional, three-dimensional image, right? The independent variables are spatial, okay? And then the dependent variable is the thing that we measure. So these are all types of signals that are a little different than, you know, what we normally think of as a signal. And, you know, I will just point out that throughout this course, we're pretty much going to be talking about signals like this, but keeping in mind that there are other possibilities. Okay. Oh, let's try something else here now. So one of the things I'm using you all as guinea pigs in using some of the different Zoom features and some of the different online features that we have available. So now I'd say, go ahead and in the chat function, let's write down some examples of biomedical signals. So go ahead and type those in and sure, E blank G, there's lots of E blank G, right? EOG, that's one. Give me something that's not an E blank G. Sure. pH, sure. That can vary with time, right? And within a cell, or these don't all necessarily have to be things you can measure. Blood oxygen, sure. Any others? Joint kinematics, yes. I mean, that one's a little bit weird, right? You can think of forces and shears and things like that as a function of time. Blood glucose, absolutely. Blood pressure, sure. Yeah, so those are, you know, those are the right idea. Action potentials, absolutely, in nerves. But have you noticed, so one thing that often happens is people tend to, come up with the things that we measure, certainly the things that we measure and monitor people with in the hospital or under disease states, or diagnostic measurements or things like that, MRI, sort of. Yeah, I mean, certainly any of the imaging modalities is a system interacting with a biological imaging, falls into there. One thing that people leave out, usually, because you don't think of it this way, is, right here, vision, hearing, sonar in bats. So your senses are signal processing systems, actually, right? And those are things that people usually don't throw in there, but they're perfectly valid. And we do analyze those systems in the same way, using the same math and so forth. So, okay, well, you have the right idea here, certainly. Yep, lots of good examples. Okay, thank you. Now I want to mention just a little bit about some terminology that's not going to be really important in the class, but sometimes I will refer to it. Let's do that. Okay. So, and again, some of these are things that you kind of intuitively know, but you don't have names for them or things like that. So sometimes we will refer to the region of support for a signal, and that's just defining the limits of the independent variable. So this one, the region of support, is from 0 milliseconds to 1,000, actually 24 milliseconds in this case. And that's all that means, right? In an image, we call it the field of view. It's basically, what you can see, or what part of the signal did you measure, right? And the point really is, this is the only thing we know about this signal. We don't know anything about how it behaves outside the region of support. Okay. Fair enough. That's a simple concept. We will talk about both continuous and discrete signals. And so in terms of our signal processing, we will be talking about both analog and what they call digital image processing. And that encompasses both of these things, right? So in a continuous signal, the signal is defined at all times within the region of support. And so that's kind of what the real world is about. Whereas a discrete signal is defined only at certain times in the region of support. That is, we only measure it at certain discrete times. And again, we don't really know what happens in between those times that we measured. We might assume we do, or we have a model for how we think it behaves, but we don't really know. And so in kind of looking at continuous and discrete signals, well, the real world is continuous, right? Whereas the computer's world is discrete. We often refer to these as analog signals also, and digital, which is a really bad name, but that's the name it got a long time ago, and so it sticks. We refer to these as digital signals. I try to say discrete signals, but we mean the same thing. Okay. And then we can move between these two worlds by estimating a continuous signal from discrete. Well, if you measure it at a couple of time points and you want to know what happens in between those time points, again, you might think, oh, I'll just interpolate, and that's basically what we do. But there are lots of different ways to interpolate. Going the other way, getting discrete from continuous is a process called sampling, which we will discuss. And the bottom line is the continuous signal is the complete representation. The discrete signal is the incomplete representation, but this is the only thing we can work with in MATLAB or any other computing environment. Okay. And so that's why a lot of signal processing that is done these days is all discrete for that reason. Okay. And, this is a zoom in of this signal. And the thing to just recognize is that when you plot things in MATLAB, MATLAB likes to MATLAB will by default join the points with a line, which makes it look like a continuous signal, but it's really not, because you've only measured it at these discrete time points. Okay, so again, just it's a thing to be aware of. Don't let this fool you into thinking that when you plot this thing in MATLAB that it is continuous, because it's not. What MATLAB has done is essentially interpolated it, right? It's drawn a straight, using linear interpolation, it's drawn a straight line between every point so that you can see, how this thing goes. And that's good for visualization. It's good to see how things develop. And we will usually look at our signals this way, but they're really discrete. Okay. This is totally not important, but it's in my slides from years ago. So there are autonomous signal generating systems. In other words, a signal that's generated without some external input. And that's, a lot of the body signals that we might read, right? The EEG, EKG kind of things that you gave me. They're there whether we do anything or not, and all we do is kind of try to passively measure them. Okay. On the other hand, there are non-autonomous signal generating systems that basically you don't get anything unless you apply the external input. An example of that is, well, we'll use one of the examples, an MRI. So in an MRI, you actually have to essentially inject RF radiation into the body and then listen for how the body responds. And if you don't do that initial injection, you get nothing. Okay. So those are, we probably won't even bring these up again, but they're in the notes, so they're there. Okay. And here's another thing that's going to be important. It's going to come up when we talk about random signals. So a deterministic signal is, by my definition, basically you could predict it with enough information, but you often don't have enough information. Okay. So in many cases, we might have a deterministic signal, but it has unknown properties or things like that. But it is a process that is predictable and not random. And we contrast that with a stochastic or random signal, which no matter how much you know about it, you can't predict its future values because it has some random process involved in it. Okay, and randomness basically means unpredictability. Now, you may have deterministic but unknown, meaning I don't know it, so there's nothing I can do about it. On the other hand, you may be able to take advantage in a stochastic signal of, yeah, you can't get it exactly, but you might be able to get a good guess if you know something about its typical behavior, which we might characterize with its, typical statistics, right? And what is the average value? How much does it vary? Things like that, you can take advantage of. So very often, having a stochastic signal where you know something about its random properties is better than having a deterministic but unknown signal. Okay. This is going to come up as we talk about noise. And, as many of you have probably seen in doing instrumentation and things like that, noise is one of the major problems that we deal with. Okay, so deterministic signal, so something like this, that's a cyclic process, is very predictable, right? Whereas this is a random signal, white noise that's been filtered, and you can't really predict anything about it. And then we aren't going to be doing fractals in chaotic systems, but these are things that are actually deterministic systems that look random because they're deterministic on a very small scale. Again, don't need to talk much more about that. Okay. And today we kind of try to squeeze in 2 sets of slides, so we will get there. But now it's time for, we're going to try to do 2-minute breaks on occasion. So you get a 2-minute stretch break. Stretch. I will, pardon me, while I stretch. This is also a time if you want to jump in and ask a question or say anything, you are welcome to. When we actually had class in a classroom, people would often come up and ask questions. Oh dear, that's annoying. Okay. I'll have to find another timer. All right. Okay, so now seems like a good time to have a look at the website, which I think most of you have found. So everything will be handled through Moodle. I know I have a couple of you from UNC, so thank you for joining up with us at NC State for this. Makes my life easier. I sometimes when I do graduate classes, I use both Moodle and Sakai at UNC, but for this course, it's going to be all Moodle. Okay. All of our classes will be recorded, okay, and you'll be able to find them on the YouTube channel, which this is a link. Generally it takes maybe a couple hours after class to get them up there. I do want you guys here, when we're having class, because your participation is important. But if you miss something, or sometimes people like to go back and go over something, everything's going to be recorded. Okay. Okay, the syllabi are here, which I will get to in a minute. There is a folder of MATLAB resources, which includes some data files and some MATLAB programs and all of the MATLAB examples that I will use. We will use a lot of MATLAB, if you didn't get that idea already. There are some brief instructions on assignment submission, and the main thing there is a file naming convention that a lot of people end up not using. and it's okay if you don't, but it makes my life a little bit easier. We will post solutions to assignments when they're available. Sorry, there's nothing there now. I always have to remember to clear that out before class starts. Okay, any big announcements will appear here. There is a forum, but nobody ever uses it, so not a big deal, I guess. And this is new this year. I'm trying to, since we don't have a textbook and can't really effectively use a textbook, I'm trying to compile some helpful resources with web links, and I've put a couple in here, but I'm probably gonna, maybe at times ask you guys to contribute some. Okay, so see what you can find, out on the web about things that help you understand a little better some of the things that we're doing, and I'll try to contribute some as we go too. Okay, so we'll try to build that up over the course of the class. All right, and then what we will find basically every day is scheduled, and we'll be pretty close to this schedule. Sometimes there's a few leftover things from the previous class that we have to finish up and things like that, but we stick pretty close to this. So there will be, for every day, there will be lecture notes. I will annotate some of the lecture notes as we go, and basically the annotated versions, the ones that I've written on, will be posted also as we go. And each day then assignments will come up. You'll see things about reading assignments in the Bruce book, and obviously that's not available, so just ignore those. But I didn't want to lose them, so I keep them excuse me, I keep them in the in here. And then any MATLAB examples that I run as scripts during the class will appear in here also. So things like that, right? So you should, everything's pretty well organized. The assignments are already scheduled, although they can drift a bit, we'll see. But for the most part, the real assignments will generally be due on Fridays. Okay. Let's hit the syllabus really quick. Okay. Most of you are in 412. There is a 512 also that is the same class with a slight difference, which I will get to in a minute, but 512 is the graduate level. Okay. But we do all the same stuff and cover all the same material. Okay, so basically, this is the basic information. Obviously, the best way to contact me is through email. You can catch me before class, after class. You can drop emails for appointments. We will schedule a kind of office hour Q&A to be determined. Okay, so the usual course description, learning outcomes, the things you should be able to do when we're done. We'll get to the things that you're interested in. So the homework assignments comprise a pretty substantial part of your grade. Okay, so missing homework assignments is usually a bad thing. So don't do that. Get them all done. If and I can be pretty flexible if you're, you've got a lot of work and you just can't get it in by 5 o'clock on Friday that week. It's okay. Just let me know. Okay, and I can give you a couple of extra days. Sometimes we're up against an exam and things have to get done because I have to get the solutions out and things like that. But for the most part, it's certainly, it's best to be on time and on schedule, right? But just let me know if you need a little extra time on something. I can generally accommodate you. The grading scale, this is the minimum grading scale. I can boost you up for participation and effort and things like that if I think you deserve it. There is a schedule of courses which pretty much reflects what's on the website. You must use MATLAB, okay? It works best if you have it on your own computer, and it is available to you whether you're at UNC or NC State. You can also use it by VCL at NC State, but that's not as responsive. And then the books that are reference materials, but again, I'm not going to make you go to the library. So those are books we've used before, and we will refer to things from some of those books. In fact, we use a lot of data that comes with the Bruce book, but again, you don't really need the book to use that. Okay. We have a kind of standard statements on late exam assignments and exams. By the way, we will have 2 midterms and a final, all at home. Okay. But basically, this is pretty standard language. So there's no surprises here. Okay. Generally, again, on assignments, I can be pretty flexible and we reach an agreement. You know, if you can't turn it in on Friday, then you say you can turn it in on Sunday. I say that's okay, that's fine. But that's the way we usually handle with assignments. With exams, obviously, that's a little, we have to be a little stronger with that. But again, if there's an extenuating circumstance, just let me know. We'll work something out. Okay. I do expect you to be here. I know 8:30 is early, and the class is recorded, so it seems like, you know, it'd be easy to just kind of bug out. But I would like to see you here. And I do notice when you're not here. So we'll leave it at that. But certainly sometime, you know, once in a while, things come up, it's fine. You certainly can access the recorded classes. Academic integrity. So again, standard language here, but basically on homework assignments, I know it gets a little fuzzy sometimes, but just make sure you're turning in your own work. Okay. The thing that happens more often than anything else is somebody turns in a graph that was made by someone else by copying and pasting it in their homework. And it's obvious when that happens. Okay, so don't do that, right? Make sure what you're turning in is stuff that you composed, you wrote, your words, things like that. Okay, I don't think that's too hard to understand that standard. It's great if you want to communicate with each other about how to do something, okay? Or certainly if you're hung up on something with MATLAB and trying to kind of bug it out and figure out what's wrong, why it's not working right, absolutely, you're welcome to consult with each other on that. Okay. Same is true for at-home exams, except the standard is a little higher. Generally, you're allowed to use any resources except consulting a human in any way. Okay, so you can't talk to someone, communicate with someone about how to do it. But anything you can find on the web, any MATLAB program, anything like that, that's okay. The pledge, neither given nor received unauthorized aid on this test or assignment. It will be on the exams, but it will basically say by turning in the exam, you commit to that, and it is considered to apply whenever you submit any assignment or exam with your name on it. Okay, if you can't stand by it, don't submit. And I think that's a fair way to look at it. Students with disabilities. So there is a student disability office, and generally, you know, if you are a student with a disability, you should know them. If you don't know them, you should. And so you should get in touch with them, and we can certainly make accommodations that are appropriate for any student with disabilities. Normally, it's up to the student to contact Disability Resource Office, and then they contact me. I have not received any of those as yet for this semester. But if I do, then I will talk individually with the student about what accommodations are appropriate. They're asking, because of the situation, they're asking us to make statements on the digital course components. And again, you can see that by now. Okay. Course continuity plan. Well, again, we're kind of in that right now. So last year, it was halfway through the semester, we had to convert to all Zoom, which wasn't, thankfully for this course, not too hard because everything was already there on Moodle anyway. So it wasn't too hard to do that. We're fully built out for that. So we're going fully online all semester, no plans to meet in person. Everything is available. If there is some extreme situation, we might repost online lectures from last year, but that's going to be a pretty dire situation if we come to that. There's no need for transportation. There are no labs. Safety statement is use your computer safely. Okay. And finally, equal opportunity, non-discrimination policies certainly apply. Code of Student Conduct certainly applies, and all of that. Okay. Any questions on syllabus? Okay. BME412, the only difference, get back to my website. The only difference for BME412 is the fact that there is a project. So all of this is the same. The grading information now converts 20% from assignments to the project, and the project, which we will talk more about later, but basically you will choose a topic, you will apply signal processing techniques to a problem that you're interested in, okay, and should have some relevance to biomedical science. And it has to have some basis in peer-reviewed literature, okay? So that's the idea. You will have a final report submitted at the end of the semester. Sometimes we have done blinded peer grading, but I don't think that's going to happen this time because we're going to have a pretty small group of 512s this time around. Okay, so that's the only difference with 512. Okay, and for those of you at UNC, NC State is it's much more rigid about course numbers. So 400s are for undergrads, 500s are for grads. Okay, UNC is very fluid about course numbers. Anything 400, 600 is for anybody. So it's just a very different, that's one of the places where things are very different. All right. Questions on the syllabus or how things are going to proceed? We good? Okay. Now it's time for another experiment. Well, actually, I did this last year. We're going to do a online pretest. Whoops. If I can bring it up. Okay. All right. So this is a pretest. Things you should have learned in linear systems. Okay, so this is how you join. You can do it on your computer or on your phone. Almost everybody. One more. Okay, well, maybe someone's asleep. All right, we're going to go ahead. There it is. Thank you. Okay. There's my start was covered up. Here we go. Okay, here's your quiz. The Fourier transform of a delta function is, and yes, you get more points the faster you answer correctly. Delta function, sinc function, constant function, cosine function. It's a constant. Okay, so remember a delta function is a, well, you know, it's the little arrow kind of sticking up and basically says, okay, this thing only exists at, is non-zero only at this one time, and you take its Fourier transform, you get a constant value. Okay, that's an important thing to recognize. Okay. Here's the points. All right. Next question. The units of frequency are meters per second, radians per second, radians per cycle, hertz. Yes, hertz. Actually, radians per second is also correct. Those are both units of frequency, so everybody's on that. Okay, so either of those is a correct answer. Okay. Hertz are also known as radians per second, cycles per second. Cycles per second, not radians per second. So important thing to, we will use both of these units, but those are different units because there are 2 pi radians in a cycle, right? One time around the circle. So hertz specifically only means cycles per second. Okay. You will be reminded of that as we go. Some people are moving up. To find the output of a linear system for a given input, perform this operation in the time domain. This is all time domain now. Convolution, correct. Yeah, integration is a, you know, you have to integrate to do convolution, but convolution is the answer we're looking for here. In time domain, we convolve 2 things. In the frequency domain, what do we do? Multiply. We multiply in the frequency domain. Correct. Remember, convolve in time domain means multiply in frequency domain. And actually the opposite is true also. We will have an application of that, but not right now. Okay. All right. True or false? Low frequency features change very quickly in time. Yes, false. Low frequency features are things that change slowly. Okay. High frequencies, if you think of a high frequency sinusoid, things have to change much faster in order to account for that. Okay. For some reason, Drew F is on fire. I don't know what that means. Okay. True or false? This is the frequency response characteristic of a low pass filter. Yes, a low pass filter. The low pass filter allows low frequencies to pass through, but filters out high frequencies. And so it drops off at high frequencies. Okay. True or false? E to the minus jx equals cosine of x minus j sine of x. The Euler relation. This should be, well, again, we will refer to this from time to time, but from doing complex math, and yes, some of you might know it as I instead of J, but yes, this is true. Okay. Good. By the way, yes, I was trained as an electrical engineer originally, and electrical engineers use J. Physicists end up using I, and mathematicians use I. Same thing, and I don't care if you use one or the other, but yeah, that's how I do it. Okay. True or false? Magnitude of a complex number quite right. Very good. So yes, it is the conjugate sum, or the quadrature sum, excuse me, of the real part and the imaginary part. Okay, good. Okay, 2 more questions. The Laplace transform is a special case of the Fourier transform. No, that one's a little tricky. It's actually the other way around. Okay, so clearly, you know, you learn that they're related and so forth, but actually the Fourier transform is a, or put it this way, the Laplace transform is more general than the Fourier transform. We will be focusing on the Fourier transform, and I'll explain why that is later, and we'll look briefly at the differences between them, but we will be mostly using the Fourier part of it. Okay. Yeah, that might have mixed things up a little bit. Okay, last one. This signal is input to a low pass filter. Which best describes the output? You get a little more time to think about this one. Oh, we're all over the place. That's a tough one. So what will happen is actually it will increase slowly and then decrease slowly after 1 second. Reason is those sharp rectangular transitions require lots of high frequency content because it requires a very fast change, okay? And so when you put it through a low pass filter, the low pass filter can't handle those very fast changes. It doesn't pass those very high frequencies. So it's going to take it longer for it to come up, and then it's going to take it longer for it to come back down. So there you go. Okay. Let's find out. Drew, third place. First place is Ben. Okay, well done, you guys. Good job. Okay, so hopefully you can see. Yeah, it's okay. So we can kind of see where we are, right? You get most of the stuff from linear systems is, you know, clear and still in your minds, but we're going to talk more about it anyway. And because it's important to kind of set the environment and make clear, you know, what's more important. Some things are more important than others. Let's put it that way. Okay. We have now, I want to mention a couple of other things. So, for under today's section for the Moodle site, there's a doodle poll for me to schedule a virtual office hour, basically trying to fit your schedules to find a time when hopefully all, but if not all, as many of you as possible could join in if needed. I've set the doodle poll for just Wednesdays, Thursdays, and Fridays because what I found in the past is with assignments due on Friday, people prefer to have office hours close to the due date when the assignments are going to be. And if we have it earlier in the week, nobody will jump in. So we're going to try for that. So we're going to try for sometime on a Wednesday, Thursday, or Friday as a kind of a standing Zoom time office hour. And then we'll see. So please respond to that before we meet again on Thursday. Also, I'd like to have just one-on-one meetings with each of you since this is a small class. So normally this class is about 3 times this size, okay? 2.5 to 3 times this size. We normally would have 25 to 30 students the last few years. But since we've now changed to this new curriculum, everything's up in the air. We don't know exactly how things are going to shake out as far as, among other things, how many students are going to go into the instrumentation area. When we first started the program, relatively few students went the instrumentation route when there were 3 options. And then it grew to be about 1/3 of the class, and now it seems like it might be going down again. So we'll see. In any case, since, you know, I mean, it makes my job a little easier, right? Less grading, but gives us a little more of a chance to connect a little bit. So this is a sign up for just a one-time one-on-one meeting, just so we can talk to each other a little bit one-on-one without recordings and stuff. So please do that as soon as you can. Okay, and then basically, you know, whatever your sign up time was, just jump on this Zoom, because this Zoom is going to be the Zoom code we're going to use for the whole class, for everything to do with the class all semester. Just jump on at that time and I will be there, hopefully, probably. and we'll talk for a bit. They are half-hour slots, but they probably won't take that long. So, okay. So that's a thing I would like you to do. All right. And then there's also an assignment 0, meaning it's not actually going to be graded, but it's mostly going to verifying that your MATLAB is up to snuff for what we want to do here. So just follow those instructions and submit your assignment through the Moodle. Before next time, that it's easy. It won't take much of your time, but it's something I would like you to do. Okay. All right, any other questions? Okay, then we will jump over to the next set of introductory topics. Okay, so we talked about what is a signal and some of the things about signals, and then we'll talk about signal processing itself. So my definition, this is from the book a book we used to use, which is a really complicated definition that we won't pay any attention to right now. Basically, signal processing is transforming one signal into another, hopefully with more desirable properties. Okay, that's how I look at it anyway. So the key thing, one of the key things here is transforming one signal into another, right? And so a signal processing system performs a transformation of a signal. It changes it, okay? And when we talk about systems, they have inputs and outputs. Okay, so we will, I will illustrate with these little flow diagrams. And so a signal processing system is, since it does a transformation, it's characterized by a transformation operation. And one way we can write that mathematically is with this kind of general T bracket thing being a transformation of whatever's in the brackets, okay? And so we can define the relationship between the input and the output that way. This is a general way that a mathematician might write that. And we haven't said anything about what happens. And in fact, there may not even be a mathematical representation of what this is, okay? But whatever operation happens here, it could be a computer program or something like that. This represents it, okay? So it's a little abstract, but that's what we're going with. And so if this is a linear transformation, then there are certain properties that it has, and that's a linear system, right? And almost all of you had a course in linear systems, so that's okay. But recognize not all systems are linear. In fact, most systems aren't truly linear, but a lot of times we model them as linear to make things easier. Okay, that's why we spend time with linear systems, because even when systems aren't truly linear, we can, over a certain range of operations, we can approximate them that way. And the math and everything else is easier. And then we also have a language we can use to kind of describe things that happen. As engineers, you might have to design a transformation. In other words, design the signal processing system to achieve something in particular. And so, that could be electronic components like an instrumentation class, analog signal processing, or you might do it with either all-purpose or special purpose computers, which we refer to as digital signal processing. And again, we will talk about both of those things in this class. Okay, so that's about the transforming stuff. More desirable properties. Well, what properties are desirable? It depends. It depends on what you're going to do with the signal, what information you want to get from it, right? If you want to extract information, if you want to talk about relationships of two or more signals, if you want to turn that signal into a different representation, because the different representation gives you the information you want. An example of that is, you know, I don't care how this signal behaves in the time domain. The information I really want is what frequencies are in it. So I go do a Fourier transform on it to find out what the frequency content of it is. That's done a lot with EEGs, and especially in sleep studies, right? They look at different frequency components of the signal, and what happens in time is not necessarily all that informative. So overall, the job we have as engineers is to design a signal processing system to change the input signal to either enhance desirable properties or reduce undesirable properties. Okay. However, if this was easy and if this was a no-brainer, then it would just be easy to do. However, in all engineering, there's a trade-off, right? You're trading off desirable things for undesirable things and making value judgments about, what's going to be the best happy medium, the best place to be, without sacrificing too much stuff in order to get the thing you want. Okay. Engineering is all about managing trade-offs, and all of your background and education in engineering is about giving you the tools and the understanding of the science and the relationships between these systems to be able to make those judgments intelligently. That may be a different perspective on engineering than you've heard, but that's how I look at it. Okay. So it's, as a result of that, unlike a lot of things you've seen in your experience up till now, there's often not a right answer. There are lots of good answers, and some answers are better than others. Okay. So it's not a binary thing. It's not right, wrong. It's this kind of continuum of, okay, there's a lot of answers that are reasonable and justifiable, but you got to know what you're doing in order to be able to justify them and make intelligent choices. Okay, so the common things that you might do in signal processing, and we will focus on noise reduction and removal, artifact reduction and removal, that is elements of other signals that you don't want that are interfering, feature detection, finding events or finding things that happen in signals, evaluating relationships between signals, getting a quantitative measurement from a signal. And we'll mention this a little bit. It's actually a big part of the field of biomedical engineering, is modeling things, using the signal processing system concepts and mathematics to model physical systems, and especially biological systems. We'll look at that a little bit also. Okay, so considering just a couple of things, we're going to talk a lot about noise reduction, because understanding that is really kind of fundamental to everything that we're going to do. So noise is going to be random, okay? About the true measurement of the signal. In general, noise is something you don't want, right? I mean, that kind of goes by its definition. And why don't you want it? Well, it gets in the way, right? It interferes with your ability to extract information from the signal or interpret the signal. So an example of this is, then we will use this example, cerebral blood flow velocity measurement. So this is using Doppler ultrasound, and I'll probably explain this a little more another time, maybe not right now. But basically, we send ultrasound pulses in, they reflect back off of the moving material in the blood vessel, And based on the frequency shift due to Doppler, we estimate how fast the material is traveling. Okay. And of course, in doing that estimation is a signal processing system, because you send a pulse at a known frequency, it comes back at a slightly different frequency because of the Doppler shift. How do you analyze that? You take a Fourier transform, okay, and see how much the frequency has shifted, which will be proportional to the velocity. Well, you do that velocity estimate for a bunch of different pulses and at different times, and basically this is the result of estimating that velocity. Okay, so you can see kind of underlying this is a relatively smooth, hopefully, pattern of blood flow velocity, but within that there is a bit of noise and even some spurious kind of spikes, because that computation is automated and probably subject to potential problems there. So that's not real, right? That's probably, and this is not real. You would not expect like a delta function in your blood flow. And so those are things that we want to try to suppress, right? We want to be able to design signal processing filters to do that. And you filter it, right? And so you can go from this to this, which is smoother and closer to the truth, but not all of the noise is gone. And some elements of those spikes, which have been suppressed, but there's still a little bit of it there, right? So it's not going to be, there's not going to be any perfect solution to this, but we need to be able to do this intelligently. Artifacts are similar, but basically don't behave the same as noise. They're kind of deterministic and they come from something else. Okay. You'd like to get rid of it because it gets in the way. This is a EMG. We see these high frequency bursts here, but it has an artifact from the ECG. So these are heartbeats here, which we don't really want. We just want the EMG information. So how do we selectively get rid of one without damaging the other is the kind of trade-off that we have to deal with. And again, there's not going to be a perfect solution. The more we suppress these spikes, the more we're going to end up smoothing out the EMG information also. So we have to find a good place in the middle in order to deal with that. Okay, so the original, after artifact reduction, you know, we got rid of a lot of it, but not all of it. And I think I'm going to stop there because time is up. So we will just, actually there's not too much left there to talk about, so that's good. We'll just kind of finish up some of those concepts next time. When we come to the end, of course, it's, you know, fine for you to jump out whenever, but I will generally be able to stay on to answer questions or anything like that. So anybody have anything? If not, going once, going twice, going 3 times. All right, thanks for tuning in. I will see you on Thursday. Do sign up for a one-on-one session. Those start tomorrow, hopefully. And we'll see you around, okay?
Thank you.
All right, thanks everybody.
Thank you.